All right, so welcome to, I think this is going to be the first of kind of a three-part, three videos. Hopefully none of them are terribly long. And I want to kind of, the whole point of all of these is really what I want to do is I want to discuss the saltwater wedge, working up the Mississippi River. Okay. And So I guess we should probably motivate this first, but the videos are going to be, this first video I want to talk about what is pressure in a physics standpoint. You've probably already seen it in a chemistry standpoint, and of course it is exactly the same. But in the physics standpoint, we are primarily concerned with the forces involved, or the forces due to the pressure. Then once we know what pressure is, I'm going to do the estuarine circulation, and I'm going to describe basically why the saltwater happens. The saltwater wedge happens. And of course, there's a few other different shapes that an estuary's, salt profile could look. And we'll talk about that a little bit. And then last, for those of you who are not interested or those who are interested, I'll do the calculus that would explain this. And I'll explain why the calculus, as powerful as it is also a little bit weak. So usually we solve these things numerically instead of with calculus. But you do the calculus first, and then it kind of gets you going. So anyway, so let's motivate this, and let's start talking about the saltwater wedge and what's going on. So basically, if this is, the U.S., here's Louisiana, here's Florida, there's Maine, and then all at the top, right? Okay, so the Mississippi River is drained by this massive, has this huge drainage area. They say it's like 1/3 of the, so here's the main stem of the Mississippi goes up to Minneapolis, and the Missouri goes up this way. And then the Ohio goes this way. The Ohio is, generally speaking, the most important one water-wise. The vast majority of our water comes down the Ohio. And then, interestingly enough, the sediment comes down the Missouri. Okay, so one of the things that you can do, and I don't have a picture for this particular thing, is for this particular presentation, but what you can do is you can zoom in on Google Earth to right there where the Missouri comes into to the main branch of the Mississippi, and go look at that on Google Earth. Go to Google Earth or Google Maps or whatever, and just zoom in St. Louis, and you can see the sediment coming in the Missouri. You'll see the difference in the color of the water. Okay, you can't really tell that the Ohio is bringing all the water where it comes in. I believe that's in Cairo, spelled like Cairo, but it's pronounced Cairo, Illinois. Okay, so if you go to Cairo, Illinois, you can see that confluence as well. Anyway, so the Mississippi River drains this massive drainage basin, and for the last, I don't know, all summer or whatever, we've had almost no rain over the basin. And so the effect of that lack of rain is that, we've got less water coming down, these basins. And I would imagine, although I haven't looked it up, but I would imagine that primarily the problem here is going to be on the Ohio, that basically, the wet east of the U.S., we're not getting as much rain, and therefore we don't have as much coming down the Mississippi River, right? So when you have less water coming down the Mississippi River, that means the salt water, which is down by, the Gulf of Mexico, the salt water can intrude upwards, okay? Now, what will happen is, and so the explanation that you will get from a lot of people, and of course, this is a huge, let's start with why this is a huge problem. Or I guess let's start with, the explanation. So the explanation that people say is that they say the density of salt water, so that is a very bad row. So the density, which looks like that, of salt water is greater than the density of fresh water, which is true. And they say because of the density of the salt water is greater than the fresh water, then that means it just flows under the fresh water. Okay, this is like as many elementary explanations as you hear for things that are quote unquote wrong or oversimplified. This is oversimplified, but it's not wrong. It's actually a really great, it's as good an explanation as you could possibly get without going into anything technical. However, I think this is kind of a beautiful problem in that it's very interesting. And so I thought that I would do this video in order to describe it. Okay, now let's talk real quick about why this is a problem if the salt water moves upriver. The primary reason for those of you who live in New Orleans, like me, is that if this is the river, this is, the East Bank and the West Bank or whatever, and you live on one of these things and you've got a pipe coming in here and it's going over here and it goes to a treatment plant, right? So over here, you've got a bunch of clarifiers. And in fact, if any of you guys want to understand how they treat water, I can kind of give you a primer on that as well. But basically what's happening is you're pulling the water out of the river in order to do something with it. So this could be a treatment plant. Okay, and so if it's a treatment plant, then ultimately what's going to happen is you're going to get out drinking water. Okay, and it may or may not just be drinking water. Like obviously we flush our toilets with it, we water our lawns with it, we do 1,000 other things with it other than just drink it. But but the standard that it has to meet is the drinking water standard, right? These things are not necessarily designed to deal with salt water. Okay, in fact, I would forget the word not necessarily. They are not designed to deal with salt water. So if you have salt water in here, I have no doubt, I mean, I haven't looked at the math or anything, but I have no doubt that some of the salt is going to get removed. But ultimately, what you cannot have is you cannot have salt in your drinking water. Okay, and they do not have methods to remove it. And you might say, well, there certainly are ways, but they're expensive and usually require a lot of energy if you're going to remove too much salt. So this is one problem. The other problem, it's the same problem, but instead of this being drinking water, you might use this treatment plant might be for cooling water for, an industrial plant or something along those lines. Now, in that case, if you're using it as cooling water, well, you're going to leave behind salt when the water evaporates or whatever it is that's going to happen if there's salt coming into that water. And again, you're not prepared for that. Okay, so that's kind of a primer on the problem. And of course, for those guys who are in my class, since this is going to go on YouTube, anybody could watch it. Let's talk about pressure. So all of this is about pressure. Everything that's going on in this whole system, everything here is about pressure, right? It is essentially the force at work that's causing it. It's not really a force, but anyway. So let's go over here. So when you take chemistry, they do the ideal gas law. So pressure times volume over temperature equals pressure times volume over temperature. Okay, and we put little 1s, 1, 1. And so this is to tell us how things evolve. And when they do this, they say, okay, well, pressure, usually what they say, if they were to define it, they would say, okay, well, pressure is, it's the effect, or it's the quote unquote, the push. I don't really know chemistry. The push of the particles on the walls, or something along those lines, the walls of the container. Push the particles in a fluid on the walls of a container, okay? They might say something like that, okay? And so basically, so you can imagine that, so if we go back to our ideal gas law, right, if you increase the temperature, so if the temperature from here goes up, so if you increase the temperature, so if temperature goes up, then the pressure is going to go up because you've got the same number of particles, but they are, they're hitting those walls harder, right? Okay, or, if the volume goes down, okay, so the volume from here to here goes down, well, then the pressure is going to go up because now you've got more particles per unit, per area, and so they're hitting it harder, okay? Anyway, so that's all chemistry. Now, in physics, pressure is just very simply defined as the force over an area. Okay, so this force is being generated by the particles. The particles are bouncing off stuff, and they're creating, they're creating a force, right? So all the particles are hitting, and so it's causing a force. But we think macroscopically. So I don't want to think about the individual particles anymore, okay? So what I'm going to do here is I'm going to think about water in a river or a lake or anything, what we call surface water. So basically any water that's got a free surface. So here's a free surface, meaning this is air above it and this is water below it. And if I'm looking at this particular water, I just need to be aware of the fact that this surface right here can move, it can have waves, it can do whatever it wants to do. Okay, so I want to know about the pressure at this point right here. So maybe I'll just call that P. Okay. Now I'm going to assume that the pressure above it in the air is the pressure of the atmosphere, meaning, you know, again, if I were thinking microscopically, the pressure in the atmosphere is how hard those air molecules on average are kind of hitting a surface, if a surface were in the air. Okay, I want to know what's going on, however, right here. Okay, so to figure that out, what I'm going to do is, and we're doing this in physics class right now, so anybody online who wants to look at this, we're going to do a free body diagram, but instead of doing a free body diagram of something else, I'm going to do a free body diagram of a column of water that ends at the point that I want to know the pressure, right? So, so over here, I'm going to draw the free body. I'm going to draw a free body diagram of that column, and I'm going to draw it in 3D. That is not what I wanted, although I do like the look of it. I hate to erase it. Okay, so free body diagram of a column of water. Okay, and this could be fresh or salt. It's not really important yet. Okay, so here we go. So here's the column of water. And let's see. Okay, now it's got some, we're going in 3D, so I'm going to draw it like this. Okay, so now I got to figure out the forces on this particular column of water. Well, I guess first, before I do that, let's get some geometry out of the way. I'm going to call the height of this thing like that. Okay, I'm going to go down like this. I'm going to call that H. Okay, and then this right here I'll call delta X, and this right here, I don't know if I can zoom in. Let's call this delta Y. Okay, so the area on the top and the bottom is delta X, delta Y. All right, so now I need the forces. Let's get a different color. Let's get, maybe I can do black or something. Let's get black. Okay, so the forces on this sucker. Okay, so I've got a force on the top of this thing. It's going all the way to the, you know, if we go back to our original picture over here, it's going all the way up to the atmosphere. So, you know, remember if pressure equals force over area, then the force on the top is the pressure times the area. Okay, so on the top, I've got the atmospheric pressure times the area over which it's acting on the top. Okay, so that's one force downwards. Okay, on the bottom, I've got a force upwards. Okay, I guess I could kind of like draw this that little thing right there, and I'm going to call this just the pressure at the bottom, whatever that is, which is what we're looking for, times the area of the bottom. Now we notice the area of the bottom and the area of the top are the same. So, you know, cool. In fact, we could probably go ahead and we could go ahead and solve for the area of the top and the area of the bottom. We know it's going to be delta X, delta Y, and then over here it's going to be delta X, delta Y. It's the same area on the bottom as well as on the top. Okay, cool. Now we have one more force. For those of you guys who are in my class, well, we got one more force in the vertical, and that is the weight of this column of fluid, right? So I'm just going to call that, we'll call that, if we're going to keep in line with what we've been doing in class, I'm going to call that force of gravity. Well, that's the bell. So I'm going to have to go teach. I'll be back in a second. All right, y'all be easy. Okay, so I'm back. So those are the vertical forces. So we have three vertical forces. You know, we've got the atmospheric force on the top. We've got the force of gravity. Technically, it acts on the center of mass, but it's not really all that important. And then we've got a pressure on the bottom. Okay, cool. So the next thing that we have to deal with is, and we don't actually have to deal with it, but there are forces on the sides of these. So there's a force of pressure on this front face, and there's a corresponding force on this back face, which but those two cancel each other out exactly. Okay, similarly, there is a force of pressure on this side face here, and there is a force of pressure, on the opposite side as well, and those just cancel each other right out. We're not going to concern ourselves with that, mostly because those pressure forces are going to be perpendicular to the surface, and so they're not going to be upwards or downwards. Okay, so we're not going to concern ourselves with that. Okay, so anyway, it's not that they're not real; they do exist, and they do squeeze the water, but they're not really going to do a whole heck of a lot in this case. All right, so now what I'm going to do in order to get at remember the whole goal here is I want to solve for this pressure down here, is I'm going to do the summation of the forces in the vertical equals mass times acceleration in the vertical. It is customary, actually, I can't do y here, can I? because I already decided that the areas here were delta x, delta y. So this is going to be in the z direction, so I forgot here. So I'm going to call this the positive z direction, which means that this is the positive x direction. No, that's not the positive x direction. Excuse me. This is the positive x direction, and this is the positive y direction, based on kind of what I drew over here. Okay. So anyway, so if that's the case, I'm going to go over here, and I'm going to add up my forces. So the first positive force is this one. In fact, that's the only positive force. So the pressure on the bottom times delta x times delta y minus, now I got the pressure on the top, pressure atmospheric, minus, not minus, times delta x, delta y. Apologize, this is a little bit unorganized. Okay, minus the force of gravity, or the weight, equals the mass times acceleration in the z direction. Okay, cool. So usually at this point, we're going to want to start expanding these things. This is already expanded. This is already expanded. So I'm just going to recopy that. P delta x delta y minus P atmosphere times delta x delta y minus. Okay, now this force of gravity, I'm going to go ahead and just write something about the force of gravity over here. So the force of gravity is always mass times the gravity, right? Okay, that's pretty straightforward. However, we're going to do something interesting here because I want to know the mass, and I want to know as a function of the density. Okay, so you may remember, so the force of gravity equals, well, mass. So if I took the density, right? So let's keep going over here. The density is, now you're probably not used to that symbol. That's the Greek letter rho. But the density is the mass divided by the volume of the object. Okay, so I can rearrange this, and I can say rho times the volume equals the mass. So if I switch sides on that, mass equals rho. Now the volume of this particular cube or rectangular solid here, of this particular thing right here, well, it's got a height of h, and it's got sides of delta x, delta y. So it's delta x, delta y times h. Okay? So if I plug that in over here into the force of gravity, okay, I'm going to get the density times delta x, delta y, h times g. Okay, so that's the weight of our column of water. Okay, so I'm going to go over here. I'm going to just kind of keep that in mind as I go over here. And I'm going to subtract the weight of the water, which is going to be rho times the volume, which is delta x, delta y, h, that's the volume, and then times gravity, right? So remember, this is just mass times gravity. Okay, and then we'll say equals, and in this case, this particular thing is not accelerating, so I'm just going to go ahead and call that 0. Okay, now what's really cool about that thing coming out like that, and so things are equaling 0, is all this delta x, delta y business. It's just going to cancel right away, right out. Okay, so now I'm left with, let's see here, P minus P atmosphere minus rho hg. Okay, and I'm already feeling pretty good about this, equals 0, because I know where we're going. And so I can say that the pressure, or minus P ATM, equals, and it's typically written in this order, rho GH. I don't really know why it's always written in that order, but usually that's the order that it's written in, right? So algebraically, this is the case. Okay, now it is customary, so now I have to say one more thing that will be unusual to you about pressure. It is customary to treat the atmospheric pressure as 0. Okay, it is not actually 0, right? Technically, it's 101.325 Pascal. I can't remember, kPa. Yeah, so typically there's two ways you can do the atmospheric pressure. So one is you could say the atmospheric pressure equals 101.325 kilopascals. The other way is you can say, well, the pressure in the atmosphere is 0. Okay, now what gives here? Okay, so what gives here is that this is what's called a gauge pressure, and this is what's called absolute. And basically, this is what the pressure actually is, And this is, we're just going to treat it like 0 because we're just basically going to reset our scale so that 0 is at a new point. And the reason that we can do this, and the reason that we're going to get away with this, is because every single place where we might take a pressure, the pressure is always going to be like, let me rearrange this expression right here. Pressure equals P atmosphere plus rho GH. So everywhere where I might take a pressure, okay, it's always going to be increased by the same amount. Whether that amount is 0 or 101.325, it's the same everywhere. So what I really care about is I care about difference of pressure. So if I have a pressure at one point, let's suppose we're looking at the Mississippi River, and I have a pressure here, and I have a pressure here, and I'm trying to figure out if the water is going to flow that way or if the water is going to flow that way. And it depends on which one has greater pressure. And so if this is pressure 1 and this is pressure 2, I might do P2 minus P1 in order to determine which way the water is going to flow. Well, if I subtract those two out, then this PATM is just going to disappear because it's going to be in both terms, right? If this is pressure 1, and then if it's pressure 2, we would also have PATM, so it doesn't really matter, right? So that's the way they do this. So typically, we would say that pressure 1, or really the pressure at any given point, is rho GH, okay? And now this is specifically, this is for a gauge pressure, meaning that if I have a pressure of 0, that means I'm at atmospheric pressure. It also means you can have negative pressures in this case, because it just means you're below atmospheric pressure. Okay, in an absolute sense, you cannot never have a negative pressure. Okay, so that is the result that we. Okay, just to set you up for the next thing, what this tells you is it tells you a few things. Okay, 1, H, that's the depth. Okay, remember this is the distance you are from the surface of the water, right? So that's how far down you are. Okay, so H is how deep you are. Okay, so notice that this particular pressure increases linearly with H, which means, like if you're like, okay, so here's my pool, okay, and I'm, I don't know, I'm 10 feet deep or whatever, okay, my pressure increases linearly. Okay, that's my pressure. Okay, if I go twice as deep, I don't know, count some boxes or whatever, if I go twice as deep, I get twice as much pressure. Okay, pretty cool, right? These little arrows are what would indicate if you had a wall right here, like what the wall would feel. I typically think of it instead, like let's suppose I'm swimming at this depth. What am I going to feel? Well, I'm going to feel an arrow of this size hitting my head at all sides, from all sides. So like let's imagine I'm like right here. I'm going to have an arrow of that side going like this. I'm going to have an arrow of that size doing this from all different directions, squeezing my head and maybe giving me a headache, right? Ideally, these arrows would all be the exact same size, okay? So that's one cool thing, okay? This is how dense the water is, or how dense the fluid is, okay? And so the way that plays in is that basically could be thought of as the slope of this line, right? The G is constant, so this is the slope of this line. So if the fluid is ever so slightly denser, let's suppose, or it's a lot denser, the line might be like this. This is for a denser fluid. Meaning, if you go way down here in a denser fluid, like let's suppose instead of swimming in a pool full of water, you decided to swim in a pool full of mercury. Mercury, it would actually be 13.5 times as steep. But let's just imagine, in that case, instead of having these, reasonably sized arrows pushing on your head, so now I've got, I'm in a denser fluid, so the pressure is going to be greater, okay? Anyway, so this idea right here, which is what I'm going to lead with in the next video so this is just kind of a precursor, okay? And so next video, we're going to start basically right here, and we'll see what happens. Okay, so hopefully that was helpful. All right.